Assalamualaikum. So today I'm not fascinated. So I'll be presenting the design code first for our group, which is we are doing CRC encoder and decoder. So CRC basically stands for cyclic redundancy check. So it is an error detection technique commonly used in digital communication system. So our design support both encoding and decoding operation using a parameterized architecture. The CRC top is the top module. So it connects both module. Both module means the CU and the DU. Okay. So the first right here is the control unit. So it controls the sequence of operation using a finite state machine. And then the second before the top module is right here, the data path unit, which is the actual CRC calculation will be performed here at the data path unit. Let us start from the beginning of the code. So here is the control unit. So like I say, it's not responsible for calculation, but to control the data path. So, and then we got this. It's the 7 steps of our finite state machine. So we got the idle. State of idle, waits for the start signal, and then we have the load, which loads the input data into the data path, and then we have a check window here. I forgot, I just need to use the mouse. So the check window, which checks whether the current Windows MSB is 1, and then we have the XOR state, which performs XOR with the generator polynomial, and then the next window, move the standing window to the next position, and then we have a check last, check whether all bits have been processed, and then the done state, we reach the done signal and return to idle state. Okay. And then here the always at postage clock, postage reset. So this always block updates the current state on every rising clock edge. And then we have always at the start here. So this a combination of block which determines the next state based on the current state and the input condition. And then we got lastly on the control unit. The controller generates 4 signals right here. So that tell the data path when to load data, this is load n, and then to perform XOR here, XOR en, and then increment the pointer and then indicate the complication done equal to 1. So next I'll be explaining the data path unit. So this is where the CRC calculation actually happens. So it basically performs the CRC computation. And then here, as you can see, this data width actually, our data path is parameterized, which means it's the same hardware that can support different data width, such as 4 bits, 8 bit, and 16 bit. We provide like 3 cases by changing only the parameter value. So basically, this design code can be used for the 3 bits, the 3 cases. Okay, so here the internal register. So these 3 admin register used during the computation. So the dividend stores the data being divided, and then the PTR, the pointer, tracks the current position, and then data hold rate is a data register that preserves the original input. Here, the current window. So actually the data path extracts 4 bits sliding window from dividend, and then this window moves 1 bit at a time across the data, and then we have right here the XOR result. If the most significant bit of the current window is 1, and then the data path will perform an XOR operation with the generator polynomial. So here, if load and again, during the load phase, if mod equal to 0, the encoder loads the input data and appends 3 zeros for CRC calculation. If mod equal to 1, the decoder loads the received code bit instead. And then else if XOR in, whenever the controller enables XOR, the current window is replaced with the XOR result. So here is pointer right here. So the pointer will increment, allowing the sliding window to move across the entire data. And then now we are entering the CRC top, the top module system. So the top module simply connects the controller unit and the data path unit together. So from here on, okay, the controller will send control signal to the data path. Okay, while the data path returns data signal such as the current window MSB and whether the last window has been reached. Okay, and then the last, the assign code word out. So right here, the final code word is generated by extracting the original data with the calculated CRC. So we are done with the design code. So now I'll be explaining the test bench code. So we scroll down here. Okay, here the phase. Okay, here is the phase. So mod equal to 0. The first phase actually tests the encoder. The input data is encoded, and the generated CRC and the code word are compared with the expected value. Okay, and then we get into the phase 2. Okay. Right here, the phase 2 decoder clean test, which means the second phase tests the decoder using accurate code word. So we're expecting the CRC remainder to be 0. Okay, so no transmission error for the corrupted test. So here, the corrupted code word. Okay. This is like 1 bit is intentionally flipped before decoding. Since the data has been corrupted, so this RC remainder should become non-zero, right? So that confirming that the error has been detected. I will run this code so that we can get the waveform. Okay, so right here, the wave is generated. At first, when you run the code, there will be no waveform right here, so you have to get the signals coming from here. So from here, the signal that you want right here, so you like click on it and click open, and then it will show up. The system is reset. So and then the encoder begins. It is the CRC computation. I'll be showing the annotated, so it's easier to see. The first start right here, the encoder begins the CRC computation. Okay, and then here is the first done. So the red part, the first done, the encoding completes producing the CRC and the code word. Okay, and then we see at the second start. So here's the first start, and then here the second start. Okay, so the second start, the decoder verifies the correct code word, and then the second done. Here the second done right here, the blue one. Okay, the CRC remainder is 0. Here is 0, so the transmission is valid. And then at the third start, okay, this is the first, second, and then the third start, a corrupted code word will be introduced. So here the yellow part is the third done. So the CRC remainder is non-zero, meaning the transmission error has been successfully detected. Okay, and then we'll be look at the total errors right here. Total errors will be 0 down here. Okay, so the simulation completed successfully with 0 test failure. This is a 4-bit database, and then I'll be passing this to my friends others to explain the test bench on the 8-bit and 16-bit. Thank you.
Hi, Assalamualaikum. My name is Nur Yasmin Yusra, and I will be explaining about our CRC encoder and decoder for the 8-bit data width. So, similar to the 4th bit, right, we have our local parameters here. However, for the data width, we will change it to 8 bits since we want to use 8-bit data width. The P width is still 4. For the polynomial, it's 4 binary 1011. It represents we generating the polynomial x cubed plus x plus 1. And we have our C width here equals to P width minus 1, and T width equals to D width plus C width. So since our P width is 4, our C width will equals to 3, because 4 minus 1 is 3. T width will equals to 11 because D width is 8 and C width is 3, so we have 11 bit code work. So here we have our registers and our wires similar to the 4-bit one. Here we have our unit under test where we have our inputs here, so it can be so the signal can reach test bench. And here we have our always clock. We do always #10 clock to simulate and generate a clock cycle every 20 nanoseconds. So to simulate our simulation, the simulation will run inside the structured initial block, which is divided into 3 distinct phases tracked by the helper signal phase. So we have our signal phase here. So here in our initial begin, we have our clock equals to 0 when our reset equals to 1, start is equals to 0, mode equals to 0, phase equals to 0, data in is 0, code word in is 0, active code word 0, corrupted code word is 0, and total errors is also 0. Our test data is 8 bits of hexadecimal D5, and our expected CRC is 3 bits, binary 010, and here is our code word, which is 11 bits just now. So the objective for our first phase, which is the encoder test, is to test if the circuit can correctly compute a CRC for a known block of data. So we will set the mode to 0 to configure the unit under test as an encoder, and applying the test data here. We have the test data, 8 hexadecimal. We will apply the test data to data in and issue a single cycle start pulse using the custom pulse start. And we will wait for the module to finish computing at pulse edge then. Here we will have our verification, which evaluates whether our CRC out matches the mathematically calculated expected CRC, which is a 3-bit 010, and saves the valid code word into active code word for the next step. So for phase 2, we will use our, instead of mode equals to 0, we will switch to mode equals to 1 to turn the module into a decoder or a checker. And we will feed the uncorrupted 11-bit active code word into the code word in. So in the verification stage, we can check that the remainder of the CRC check is exactly 3 bits binary 000, signaling no errors were found, and confirms the data out correctly extracts the original 8-bit hexadecimal D5. Moving on to phase 3, we will still use our mode equals to 1 to install the decoder mode, but we use our XOR gate bit mask here. So the XOR bit mask intentionally will flip the 5th bit of the code word, storing it in the corrupted code word file, and it will feed the broken packet into code word in and also pulse start. So in the verification, we can validate that the CRC check returns a non-zero value. A non-zero remainder mathematically proves that the underlying CRC logic detected the single bit fault. Here to conclude our test bench, we can see the conclusion of the test. The test bench will display a summary in the simulator console window if all phases match their expected outcomes. So when the final result will equal to pass TC2 or not, it will go to final result equals to fail. So here we can see the result here is pass and TC2 8-bit test completed successfully. Now after we generate and also run simulate the test bench, we can see here we have our clock reset, our start, our mode, and all the parameters. When our reset is 1, it stays high, forcing all the internal CRC registers to reset. And also at 40 nanoseconds, it transitions to 0 to let the circuit run. So now we want to see our phase 1 where the CRC encoder, we test the CRC encoder. So here we can see when the mode stays flat here at 0, the data in changes from 0 to binary, which is 1101. 0101, and the start goes high for exactly 1 clock cycle, then drops back to low, which this pulse tells the UUT to register the data in. And then the done will stay low here, then stay low for several clock cycles while the internal state machine serializes or processes the bits. So when the computation ends, we can see when done pulses here at high for 1 cycle, we have our stabilized 3-bit binary here, which is 010, and also the code word will stabilize to the 11-bit binary, which is 1101 0101 010. So now for the phase 2, where our mode will switch from 0 to 1 for the decoder mode, which is phase 2 is the decoder phase. We have our code word in here, which is 110101 0110, which is the value that we have in our phase 1. And then for our done here, we can see it is low, remains low while the decoder divides the 11-bit message by the polynomial 1011. So when the computation ends for phase 2, we can see the done here pulses up high, which is 1, and our CRC check will display here 3-bit binary where 000, and the data out here binary 1101 So now here we can see the phase, the start is reset to 1. The start is active high, so it's 1, indicating that phase 3 is simulating, which is the decoder corrupted test. Here we can see the mode is also at high, stays at 1 because it's in decoder mode, and the code word in here we can see here it is displaying 11-bit binary of 1101 0001010, and we can see that the 5th bit from the right has flipped from 1 to 0 due to the XOR bit mask in the test bench.
Assalamualaikum Doktor, my name is Ashka and I'm going to present about 16-bit. So, the code uses local param to define the system specification by defining D with equal to 16, P with equal to 4, and polynomial equal to 4 binary 1011 as parameters. The test bench can be easily adapted for different data sizes without rewriting the core logic. The UUT, unit under test, instantiates the CRC hub module, making the test bench signal to the design code for simulation. The false starts. This helper class simplifies the simulation flow. It triggers the start signal for exactly one clock cycle at negative H clock. This mimics real-world hardware behavior, ensuring the CU initiates the CRC process correctly. The test bench validates the design through 3 distinct functional phases. So phase 1 is encoded test. The system is set to mode equal to 0. It processes the 16-bit input and calculates the CRC remainder. The test bench compares the generated output against the expected CRC to verify accuracy. So for phase 2 is decoder clean test. The system is set to mode equal to 1. A valid code is input. The decoder is expected to produce a CRC check result of 000, confirming that valid data is verified successfully without error. So for phase 3 is decoder corrupted test. The system remains in mode equal to 1. The test bench intentionally flips a bit in the code word active code word 19 binary 0000000100000 to simulate transition corruption. The successful design must output a non-zero CRC check, proving it can effectively detect error. Okay, so this is the waveform for 16-bit. The waveform illustrates the communication between the testbench and the SSM using the Dan signal as a relationship. The testbench waits for the Dan signal to go high before evaluating the output registers. This ensures that data is only read once the SSM has successfully completed its calculation cycle. So for phase 1 is encoder. The system set mode equal to 0 to initiate encoding. The waveform shows the CRC remainder being generated at CRC out only after the Dan signal passes. So phase 2 is clean encoder. The system switches to mode equal to 1 by looking at the CRC check line in this waveform. You can see remains at 000, confirming that the clean code word has verified successfully. So for phase 3 is corrupted encoder. The test bench introduces an error into the code word in this waveform. Observe that the CRC result immediately becomes a non-zero value, proving the FSM successfully detected the corruption. So that's all.